So it's a fun little puzzle that you can do with your body, and you can have your students do it with their body. So you hold your hands up with your thumbs sort of facing, and then you hold them straight out with your thumbs going straight out. Right? Then you cross your right hand over your left hand. Then you turn your thumbs so that they point to the ground, and you interlink your fingers, and you wiggle your pinkies, you wiggle your thumbs, and now you turn your hands straight. So how did that go? So I'm seeing some people kind of laughing and looking at, hey, something went wrong, you know? It's like, wait, how did you do that? There's actually a mathematical story behind that and a reason. The mathematical story and idea is one great problem-solving technique is to work backwards. In other words, go thumbs up, cross, thumbs down, wiggle, wiggle, turn up. What was the very last thing we did? And see if you can do it backwards, and you can feel where your hands were and then figure out what happened. And so, you know, we didn't end in this sort of locked up position, right? We had our hands here, and where were we before this? So this was the end. Where were we before we ended? So you all do it forward.
Inside.
So I do hands here, I cross, I go thumbs down, and I intertwine. The wiggle is just kind of distracting. But this is almost the end. Is my hands are in, my fingers are interlinked, my hands are twisted over so that my thumbs are pointing down, and then I'm turning so that my hands are facing up. So the very end is my hands are interlinked and facing up. Before that, I was like this, which if you have your hands kind of linked together, this feels rather different than what you did before. This is more uncomfortable, sort of a morning stretch. And then we can unwiggle, you know, we can wiggle and unlink and then turn our hands. So I'll let you think about that. I think it's probably time for me to start a math session. Yes? Are we ready to roll? But you understand, if you think about what I did with my hands, it might take a little while to practice and figure out how to do that. But if you work backwards, you will figure it out. So let me share the screen here. And let me just minimize that. And let me drag this over and make it a little bigger. I know there's a way to make it bigger in the view. You would think by now I would know how to use tech in a virtual classroom. You know, old dog, new tricks don't work so well. Okay, so here I've got 2 copies of a museum. And the museum wants to protect their art. And so they are going to contract with a alarm company. And so the alarm company has one type of alarm that's not too expensive. It basically is a camera that they can post on to the roof of the building somewhere. And the camera has a 360-degree view. And so the question is, can you view this whole room with one fisheye camera? And so fisheye, which I'll call FE camera. 360 degrees. And so can one see, I suppose I could put C in quotes, the entire room. And so place to see this is if I go to say pencil, shape, draw an ellipse. For instance, if I put the camera right there, what could it see? Well, going in a straight line, it could go from there down to here. Oh, actually, let me escape. I'd like to put this in a different color. Let's put it in blue. Could go in a straight line down to here. Then over here. Then up. Then over. Down. And up. Oh, I'm going to do that again. I missed a trick on this. Pen options. Fill. So I'm going to do that whole thing again. If I start here in a straight line, I could see this point. I could see every point along this wall. I could see every point here. I can see every point here. I can see every point here. I can even see down here and here. You see how that one red camera, if we switch, and I'll put the red back up. Oh, I see, I'm pushing the wrong button, aren't I? That's not a circle. Okay. It's that one, right? So if I place the camera here, that's not such a good spot because, for instance, if we come from here to here and pick if we pick a point, a painting on the wall over here, the Joker can come in through a window and steal the painting and leave, and he won't be seen by the camera. Does this make sense? So, does somebody have an idea of where we might put one camera in order to capture this? In fact, I'm going to make another copy of this because we might do more than one. So what do we think? Is there a better place to put a camera where we can see everything or see more?
Probably more on the bottom, like in the wider area of the shape.
Sure. So do you mean the very bottom, like against this wall? Do you mean in the middle up here? So first, sort of in the middle here or on the wall?
Like three units up.
3 units up. Okay. And then how far to the left or to the right?
Right in the center.
Right in the center. All right. Thanks. This sounds like a great idea. Let's give it a try. So I'm going to come to pen and so let's do this spline. And so if we start right here, then we can come up in a straight line. We could see all of that. We could see as we come down here we could see as we come down here, we could see this whole wall. We could see all of this. You could see here we're starting to get to a limit of how much we could see, right? And then it comes back down. Oh, it comes back to here. Then we can see all of that wall. So, and then I can bring it back. And if I want to mark where the camera was, just because, I can mark the camera was right here in the middle. So
yeah, and then just don't put anything valuable in the white area.
Yeah, so that's one strategy. This is very, very good for one camera. One question here mathematically is, can you get all of it with just one camera? And there's sort of 2 points mathematically to this. One is you might have a guess. Guessing is absolutely awesome. You should encourage your students to make guesses and because you discover things. When you say something, if you say something that's true, it often resonates and, oh, that's right. And if you say something and it's false, just enunciating it often makes it, oh, that was a kind of silly thing to say. It's perfectly fine. You know, Thomas Edison had this quote where if I make 1,000 mistakes and then come up with one good invention, people remember the one good invention, and who cares, right? I mean, that's why not? Try things, see what happens. There's no cost making a guess. And the other point, though, is after you make guesses and think about what's happening, you should be able to figure out for sure if it's true or if it's false. Math has this thing where we don't need to debate about it. We can argue and figure out, we can make proofs. We can come up with reasons that explain perfectly that something either works or it doesn't. And that's really part of the essence of it. And so, and let me rephrase this with just one camera. So what do we think? Can we see it with just one camera?
There's one shell and one of the okay. I eat shells. I do.
Sounds like we have somebody. So guessing does not hurt, right? There's no cost to a guess. And so I want to hear at least 2 people guess, say, hey, yeah, I think we can, or I think we can't.
I say we can't.
Awesome. Who said that? Who said that? I want to say thanks for speaking up. Let's hear, is there another person that thinks, does somebody disagree? Or did we just find the source of political unity? Math, right?
I think we can't.
So 2 people think we can't see everything. Okay. Which, by the way, it looks like somebody put some annotation here, unless this was me clicking. Annotating and drawing on the screen in the Zoom, if you want to share ideas, is fine. In fact, I set up a Google Jamboard that I'll stick a link in the chat. In case you later on say, hey, I have an idea, I'd like you to see a picture. How can I share that? Well, the way you could share it is, let's see, everyone in the meeting. You can say, hey, I'm drawing on that. There's several different pages that have some graph paper or some just blank or some things with documents that we can draw as we go forward. So there's a difference about, so we just had a guess. So awesome. Let's we had a conjecture. In fact, over here, I got in the chat, so I'll give, oh. I thought somebody said can't, but I don't know who, so I can't give you credit for your work. Can't, right? But if you want to come up with a conjecture that you can't, can we come up with an argument to say that you can't? And so this comes back to our math salute and looking at working your way backwards. In fact, I'm going to make a copy of this room to put down a little bit because we'll have another question and then another question. Skip that drawing for a second. So how would you work this problem backwards? And by the way, how much of this do you suppose you could do with a third grader? Do you suppose that using art supplies and a grid, you could have them place a camera and figure out what parts of the museum it can be seen by the camera? I'm willing to bet that that is a problem, a geometry problem that you could solve in a pretty elementary grade, depending on how complicated the outline of the museum is one of the buttons you can twist in order to make the problem easier or harder. And in fact, I can think of some other questions here which we might think of and address. But how do we see that you can't see everything with just one camera? I've got a new message here in the chat. So Marlene says, for sure, thinks can't with one. Let's add this in. I like this. Oh, actually, let's do this like this. I'm going to move this and name the conjecture. Conjecture. So you speak up, you get credit. Can't with one, can with two. Awesome. Woohoo, right? I mean, this is, which actually I like praising students when they come up with guesses and come up with answers. I like getting people to do this. If you put the camera further down at the bottom, you could cover a little bit more. Oh, great suggestion. So let's put the camera down a little further and cover more. So let's go to draw and spline and maybe put it all the way down. How about put the camera here? And then we could see everything in there. 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 Oops, not there. Control Z, Control Z. Oh, oops. Control Z. And I lost my.
What about if you're saying it's a building? This is Bertha Elkriver, I'm sorry. You're saying it's a building and all cameras are from the top.
So partly I'm making this a two-dimensional problem, and so that, you know, the camera, I'm putting a dot and I'm connecting with lines. We could certainly make the three-dimensional analog of this question. But it's nice, and so, yeah, which works well if the building is just a flat floor and a flat ceiling and no balconies, then it really looks like the two-dimensional problem. You put the camera on the ceiling and it can then look at everything in its line of sight. And so then what we're doing is we're looking at this, we're looking at the blue color, and we're looking at the spline. We're putting the camera on the bottom. And if we put the camera on the bottom, we can come up like that all the way up here. So indeed, it looks like the triangle on the top that's missed looks to be a little bit thinner now. And there's another triangle that's missed on this side. So, you know, my lines aren't perfectly straight, but I think we're getting the idea of what this means. And if I switch to put the ellipse for the camera and put the camera. So, yeah, we were able to cover a lot of the room with just one camera. If cameras were very expensive, this is probably a pretty good thing. And so partly it depends how expensive are the cameras versus how expensive is the artwork. Maybe come down like this and
David, this is Linda. So going back to the question, you know, it's okay. So you were to see the robber, okay? So putting the camera with those two other images that you have, and would you still be able to see that robber?
So let's put it, let's put in a joker and see. So coming over here and we're at an ellipse, you know, so maybe we'll put in Harley Quinn. If Harley Quinn was right here and the camera was here and the diamond necklace was stuck right in that corner of the museum, when the camera tries to see, if the camera does not have radar, you know, if the camera can't see through walls, when the camera tries to draw a line straight up to Harley Quinn, this corner right here of the room blocks it, and so Harley can't be seen. Does that make sense?
This is Shelley from Kayenta. We didn't mention if the camera was going to be stationary, so could we use a roaming camera where it follows a track from side to side?
I like it. And so we're changing the problem, which is always a very, very cool thing to do. I'm actually grouping your question of if the camera moves to the question with the roaming camera, because if we could see it all by putting a camera here and a camera here, or, you know, by one camera here gets this square, another camera gets this square, a camera in the bottom gets everything in the bottom rectangle. So, you know, maybe it looks like we can cover it all with 3 cameras. You know, so you see how I'm arguing based on the pictures that I've drawn. This camera, the very first camera we get, gets the full square on the left. An analogous camera placed here could get the full square on the right. And a camera in the middle would get the whole rectangle on the bottom. So if you had a moving camera, instead of 3 cameras, the camera could start here, take pictures, then it could move to the bottom, take its pictures, then move to the top, take its pictures, and move back and forth. So it would see everything, but there might be times when there are parts that open and close that would allow something with the moving cameras. So the moving cameras are similar to the multiple cameras question. So I don't know if my video is up, but what was the moral of my twisting hands and looking like versus doing this? So what was the mathematical rule that we learned or trying to learn here?
to work backwards. So looking at or creating a center point where there's a filled circle and then placing the map on top to see where it could have the most coverage.
Woo-hoo! Yeah. So what I really like in math is not telling people, to some extent we have to teach people how to add and subtract and do fractions because they have to know that, do further things. But, you've got your smartphone. The smartphone will add. Far and away, the more important thing about math is how to think clearly about things. And so thinking techniques like working backwards or trying examples, are much more important than adding and subtracting, because you're going to be thinking much more than you'll be doing math. And so working backwards is, instead of looking from what the camera can see, might be saying, if I start with a piece of art, a necklace in this corner, where would we have to put cameras to see this particular corner? So I hope you see the mouse moving here. So in fact, we'll say this, where would a camera see the blue and in case you're wondering what the blue corner is, oops, that's not blue, is it? That looks more like blue. So how do we figure out where the camera has to be to see that blue corner? If I put the camera over here where my mouse is, would that see that blue corner? So if I put the camera right here in the middle, set camera where objects are to the corner of that area, and we see no, it doesn't. Yes. And so in fact, what we can do is we can shade in all of the places where we could put a camera that could see that corner. And so if we shade in those areas, we might get something like a camera going along this line can go straight up and see the corner. A camera over here can see that corner, going in a straight line like that. If the camera's up here, it can see the corner. If the camera's over here, in any of those yellow areas, I can see that blue corner, but in any of the white portions, I can't see that blue corner because it's obscured by either this wall or this wall. Does that make sense? And so then if you want to see, can you do it with just one corner? Well, if one camera had to see the entire museum, it would have to see this corner and it would have to see this corner. All right. So if you're going to see those two corners, if you wanted to see, say, the purple corner, the purple corner is going to be seen by, say, the orange. And the blue corner is seen by the yellow. And so there's no way, since the orange and the yellow do not overlap, there's no way that I could place just one camera that could see both. Does that make sense? And so this conjecture is in fact true. See below. Right? Do you understand the argument? In order to see the blue corner, the camera would have to be in the yellow. In order to see the purple corner, the camera has to be in orange. And there's no way that the camera can both be yellow and orange. Wow. People should learn to spell too, huh? So let's come to part of our conjecture was that not only could you not see it with one, you could see it with two. Huh. It seems like I've argued that we can't see it with one. What would I have to do to argue that we could see it with just two cameras? So how do you prove that you can protect a museum with just two cameras? If I'm the camera salesman and I've got blueprints of your building, what should I do?
You could place them in the bottom corners.
Ah, I like it. Thanks. That's Monica, right? And so if I place one camera, so let's try it. Let's place a blue camera. Maybe even just over here, and place a purple camera just over here. And then if we want to see what the blue can see, the blue camera sees everything that's in its line of sight. So I could start there, and I could come to here, and I could see up to here, up to here, up to here, up to here. Kind of misses that corner of the building, so that's kind of a bummer. But that blue camera sees quite a lot, right? Now, if we want to see what the purple camera can see, I can color that in green and do exactly the same trick. So I could start here and come down and over and up. It's not going to see that triangle, but that's okay because that triangle is already covered by the blue. Notice this is a straight line from the camera to this corner. So this corner on the right-hand side can see that corner of the museum, which is exactly because that camera on the right was in the orange region. And then we can come across and come down, and that's a complete proof that those two cameras see everything. Does that make sense? Do you think your students would like playing with this? Is this something that, and if so, what grades would be playing with it? Who could you have thinking it? Are there adaptations you could make?
I think definitely the skill development of working backwards is applicable to any grade level. And I can first see it in the high school as a freshman teacher as maybe a workshop of thinking backwards is okay and guessing and trying examples. It is a skill that is very rarely practiced.
Yes. It's really, you guys have an incredibly hard job, as people are a little starting to see with the COVID, but you know, there's all the tests that the students have to do and all of the curricula, all of the material that they have to cover, and yet you still want to inspire and show ideas at the same time. How do you balance it all? I know that some teachers will mix in just, you know, I once taught a class for education majors where I did all, quote, fun activities. And at the beginning of the class, people were really excited and kind of liked it for the first couple of weeks. And then they started thinking, hey, wait, but am I learning, you know, practicing the fractions? Am I practicing how this works? And they started feeling really uneasy. And in fact, it did not work well at all. I've also taught classes where I've done no fun activities and just the material. There's a gray area in between where you should do some of this practice and drill and also some of the things that are out of the box and different that just mix things up a little bit. You notice I have an extra museum here. The reason I have an extra museum is there's another alarm company in the business, Wayne Enterprises. Has an alarm that bounces off the walls, has a oh, that's a statement of fact, not a, right? In other words, if you put the alarm in this corner here, it could come up and send a sonar signal that would hit this wall and bounce, and then it might hit this point. And so using just one straight bounce, the Wayne Enterprises could actually see, well, I don't know, can the Wayne Enterprises alarm see the whole room?
Would that depend on what degree it bounces off?
Yeah. And so in order to understand that, let's understand what this bounce means a little bit more. Okay. So if we want to understand what this bounce means, here I've got this picture. Maybe there's a divider in between these things. So let me stick a line here. Like, there might be some wall over here so that there's no direct line between this camera and this ruby. And so what you're hoping is that you could get a sonar beam that would come from here, hit the wall, and then come up like this. Question is, how does the sonar beam bounce? And so it turns out that the way a sound wave bounces is it will get from one point to another point in the least amount of time, which equivalently, if you've got, you know, air is all the same temperature, it will get from one point to another point in the shortest distance. And yes, it's also doing pool or using a laser that kind of bounces off the walls. And so it's pool shots. If I was trying to do a bounce shot on a pool table and there was some ball in the way here in a corner over here, I can't just hit it against this wall arbitrarily. If I hit it here and come on up, I miss. I have to be a little like Eddie Felton against the Minnesota Fats, and I've got to find exactly the right place to shoot the red ball to make it hit the green ball. Any idea of how we could figure out a way to figure out the distance of a curve that goes from here to here to here, and compare that to a curve that goes from here to here to here to find the longest or the shortest one? Let's stick in different colors. So for instance, one possibility might be this. But I'm not sure that's the shortest way to get from the red to the green. In fact, computing that distance is a little awkward. Does somebody have an idea of what we could do to recast this to get a different line that was this distance?
Sir, what about using corresponding angles?
So what would have to happen with these angles?
Corresponding angles are usually congruent. So using one point to another, equal angles might be able to hit the green one or overhit it.
Right. So how do I make, so this was done poorly. This angle here is not the same as this angle. This is much bigger. But how do I make the angles the same? It's kind of hard here in the drawing. I could estimate. I could try another line in a different color. I could try going from here to, maybe here and then over to here. That looks closer, but is this angle too big or too small? And how do I know? Just kind of get the sense of it because you spend enough time in a pool hall. But here's a hint. This is a place where you could use symmetry in order to change the picture by get something that would have the same length. Can you see a way to use symmetry to get the same length?
Wouldn't you find the midpoint of the red dot and the green dot first?
Find the midpoint. There we go. So you mean go a line straight between these and find a point somewhere over here that's halfway in between. So what do you do once you find that midpoint? In fact, maybe it's going down one and it's going 2, 4, 6, 7, 2, 4, 6, 7. So in fact, that is the midpoint. I'll mark it. Okay. So I found the midpoint. There it is.
Has to be a straight line.
So oh, did I not? Oh, yeah, that's not the midpoint. No. That would be the midpoint, right? It's going down one. So move the green dot in the same distance as the red against the dividing wall. What do you mean by, so take this green dot here. What do you mean move it same distance? You mean put it up here? So that would change the problem, right? If the green dot was here, then the two dots are symmetrical, and so the place you should hit should be the symmetrical place, cutting it just halfway in between. Rotate 90 degrees clockwise. Rotate 90 degrees clockwise about what point? What center would you use?
If this is Myrna, sir. If we can move, can we move green dot? If we can move green dot, then we can set this an image of the red dot, wherein we can rotate this red dot 90 degrees clockwise. And the point of rotation is about here. About here. I don't know.
Are you? You want to try
at 0
drawing
and
up?
The point of rotation must be at this point. Sorry, but I
Oh, so you're rotating around here 90 degrees.
Yeah.
And so that would be taking the green dot and putting it, sort of 3
It should be in
and 6.
The green dot would be here.
And how does that help get the, I like this. This is the idea of geometric transformation like this is indeed going to be the right. There is something to this. But somehow, if I'm taking a line and I'm putting it to here and then it comes up, there's something instead of having this line bounce, what would be nice to have happen? So I claim kind of an interesting thing to do would be if the line went like, somehow if it
Morning.
continues, yeah.
I want to suggest something. I don't know if this will work, but for me, I might find the distance, the shortest distance from this point to the blue line, which is this line, the vertical. And then the shortest distance too from the green dot to the blue line. And then this vertical lines, the distance of that, I will find the midpoint and make 2 right triangles. And find the diagonals using the Pythagorean theorem. I'm just thinking that might be the shortest one.
Yeah, and this is making these constructions is giving some extra ideas, right? Guessing kind of helps. There is something that's going to get you an equal angle by the congruent. So there's something you could put this point. So if you see this light green comes from here to here, is there another point on this dotted line? Request live transcription, enable. Yes. So is there a another point on this dotted line so that the distance from this reflection point up to this green point would be the same as the distance from this reflection point to something else on this dotted line? Where would I move this green point? If we're looking for, make the line solid again. If I wanted a gray segment going from here to here to be the same as a segment from here to some point here, where stop me, is it the same distance? Is this bottom gray the same distance? Too short, too long, just right?
Yeah, 3 units below the blue line.
And so what did we do with the green dot in the blue line to get to this new point?
Reflect.
Ah, we reflected, yes. And now, if you look at this light green followed by this gray, is that the shortest distance going from the red to the gray?
No.
Ah, so what would the shape be of the shortest distance from the red to the gray?
Connected with a straight line.
Yeah, so let's put that in. So let's pick red and, oh, yeah, we can do red. And let's switch to a line. And if we go from here, actually, I'm going to stop that for a second. I'm going to make it a dotted line or a dashed line going from here. That's the shortest distance. In fact, in the math club, we were doing an activity on reflections here at K-State. We played pool as we were talking about the activity. And I actually used this trick to make bank shots where if I wanted to do a bank shot like this, I put the chalk off to the side of the pool table over like this. And I aimed at the chalk instead of at the ball so that my cue ball hit here. And then by the reflection, it made the triangle that you see on this side reflect up, which in fact, if I switch this now to a standard, and if I make it into actually, I'm going to do it just with lines so I don't turn on the shading again. If I come from here down to here, and then from here to there, that red path is the path that goes straight from the red to the green in the least distance. We know that goes in the least distance because this red line has the same length as this dotted segment because they're related by reflection. And if I drew this on a piece of paper, I could just turn the piece of paper over or the transparency, and you'd see I wouldn't be changing the length of the line. And making those the shortest distance will in fact imply that this angle will be the same as this angle. So there's a little bit of a geometry problem to prove that. Does this make sense how this reflection works?
Yes, it does.
But
The question I have is, if we're sending the sonar from the red to the green, does it work the same way from sending the green to bounce off and go to the red?
Ah, excellent question. And so in fact, I can take this whole picture and I can reflect it across this blue line. And so let's do that. Woo! Awesome question. I can do my happy dance here, And so let's make it's not completely obvious that if going this way is shortest, that going this way is shortest. But in fact, the distance you walk, the length of a line doesn't depend on what direction you measure it. Another argument that you could do is we could take our red circle and we could reflect it, bringing it goes down 4 points, an additional 4 points here. And then we could draw a dotted line. Joining this. So I'm not snapping to the grid, so the lines are, a little off when I look at the solid line and the red line here. That's just me not having good hand-eye coordination. But hopefully you see that because we're reflecting this whole picture, this orange line is the same length as this red line. And the path you get by doing the argument reverse goes down now this orange red, and then you reflect up the orange dot, is exactly the same procedure as you would get if we reflected the green point, put it over here, and drew the line straight, and then reflected this segment over there. Yeah. Let's see if we can use this idea of reflections, which got a little bit complicated. Maybe let me draw a picture of that again, just so that we have the basic idea. Oops. Let's make it a standard line. And let's make a standard red dot, a standard green dot, make a reflection of the green, make a dotted line, and then make a standard line. Certainly, if you're teaching a high school geometry class, there is a lot of fun. Is this triangle congruent to this one? Why is this angle the same as this? There's a lot of exercises you can do. Most of you aren't. I mean, maybe I've got one or two high school teachers here. I think we've got mostly lower grades, which Gord will help us fill in. Let me also check one other thing here. How are we doing time-wise for the session? I haven't been paying attention to that at all.
It's 10:10.
It's 10:10, and we said that we'd run this session until that's kind of in the way. So we said we'd go to 10:30. So we've got 20 more minutes. So this is the picture of a reflection. Let's come to the question we had. Does the Wayne Enterprises, let me see if I can get this out of the way. Okay. So let's come back to this question about, can we get the Wayne Enterprises sonar alarm to fill this whole room? Let's see. Edit new page. New page after. That sounds like a good thing. So, what do you think about the Wayne Enterprises alarm? Where should we try one if we want to cover the whole room?
Does it only bounce once or does it keep bouncing?
Ah, great question. So that's clarifying whether things in, so that bounces off the walls. As many times as it takes.
So you could basically just put the camera anywhere.
That's a great question. So that's a great conjecture. Who said that? I want to give you credit for it. Was that Monica or who? So let's try it in this particular example. So let's place a camera heck, let's be mean. Let's place it over here. I said anywhere. So if we want to figure out what things you can get with this one camera, a first thing that we might need to do is see what it would get with no bounces. And with no bounces, we've already kind of seen how that works. You just draw the straight lines from this point to everywhere it gets when it doesn't cut through a wall. And so that's going to get us a collection of segments. So it's going to go from here through there, continue, it's that corner. So it's not so bad, but it's still missing quite a lot. But that's with no bounces. How are we going to figure out what it could do with a bounce? And so where might it bounce? And so what might I want to do with this black room? So what would be a good first bounce? In other words, what wall should we bounce off of? If we want to hit up to here.
Probably
The
some
lower one?
Lower one, sure. And from this little geometry consideration, if we want to figure out our pool shots when we bounce off of a wall, to figure out where it goes, what should we do with the picture in order to figure out what happens to bounce off a wall?
Work backwards and reflect.
Yeah, awesome. So you don't think that reflect and bounce are necessarily the same thing, but actually if you think about a mirror, yeah, the light bounces off the mirror, the sound waves bounces off the wall, the racquetball bounces off the side, or the tennis ball bounces off the court, reflects off the court. In language, that kind of works. So what we really want to do here is we just want to reflect. And so we can type in the words bounce equals reflect. Right, if you get what I mean. And so to understand the way that works, let's go to more drawing tools. And I like the spline, but I want to change the tool just a little. Pen options. I want to turn off fill for a second. And I want to make this thing dashed and black. So I'm going to reflect this whole museum across this wall. So it goes 3, 3, 3. So I'm going to come from here, 3, 3, 3, to here, to here, to here, to here. So this isn't really part of the museum. Oh, that's kind of weird. Why did it do that? All right, so I don't know why it had that little funny thing at the end, but it did. If we want to see what it does with one bounce, I can change the color, and I can change so that we then fill again with the pin. And so now in looking at the bounces, I can come from here like this. So and in fact, when I then reflect this region across, you see that I'm filling up the whole line from here to here. Oops, nope. Escape. Control Z. It was useful to, I'll do that in 2 separate segments. Yeah, when we're in person again, I'll be able to provide coffee for our workshops. So this, we certainly covered this green triangle that we see in the actual room with the blue already. But what this is showing us that in the reflection, if we take this funny shaped region that's colored in green, we get all of that in one reflection as well, which I can see that region maybe drawing it with an extra set of lines. It comes from here and it comes straight up like that. It comes over. So that was reflecting the line going beneath it. Then it reflected to hit the other corner here. It went, continued going, actually, we got a much bigger spot. We started from the spot in the middle and we went up. So in fact, it went so that it covered that much. Oops. And so now we're covering all of that using just a bounce off of the bottom wall. What do you think? Is it going to cover it all? We can do as many bounces as we like. So instead of just bouncing off the bottom wall, if I want to come, oh, I need to come back to where I started here. If we wanted to cover the whole museum, could I get something using, instead of 2 bounces, 3 bounces, and fill in this extra triangle? So, just maybe it's worthwhile for me to stick in a bounce to show how we get a point in a straight line while we do this. And this got a little complicated. I'm hoping not too complicated, but we can go from here down like that, then from here to here. That purple path is how we view that one point of the museum with one bounce. And so all of the gray points are gotten with one bounce. The blue points are gotten just straight line of sight. We still have this extra triangle. So if I was going to draw another purple or orange or red path that tried to bounce like a racquetball or a pool ball with a funny obstruction in the middle of the pool table, where should we aim if we are trying to get to this white triangle that we're missing? So 3 bounces, I'm getting people saying 3 bounces. So what 3 bounces? So what wall should we bounce off first? What wall should we bounce off second? Whoops. Bottom. We'll get So what wall do you think you want to go off first if you're making your pool shot and you're trying to get to this white triangle?
In the chat, there's a comment, lower second from right, then to the right wall.
Lower second to the right, and then the right wall. So we're going to go, so we're first bouncing off this bottom wall, just like we did, but then we're going to continue bouncing off this wall and try to come up like this. This seems like a really good idea. I like it. And so then comes the question, how do we construct it? Well, we can construct it using reflection principles, just like we had. And so to do these reflection principles, when it's coming down like this, I want to see this third copy. So I will change so that I'm drawing, I'll try the splines again. I'll try gray. I will try dots. And so I'm going to come from here down here because I'm reflecting over, oops, escape. Control Z. I want to turn off the fill. Gray. It comes from here, 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 here. See that? And so the thing that we're trying to get into is the reflection. We're trying to get over here, right? This is our goal. And maybe I'll mark a point there. Oops. Right. Our goal is to get here. But by reflection, that's the same as getting here. But by reflection across this wall, that's the same as getting here. Does that make sense? So that means that if I draw a line that comes from here straight to the point that I want to see, like that, I can then see what that's doing when I reflect all the way over, which it's a little tricky to see what that reflection is going to be. That reflection this reflection is going from this point where it meets this wall down here, which isn't a real reflection, which isn't, that's not really hitting a wall. That's in the image where we've made a reflection. And then when I want to see what this is all doing in the final solid path, this is a path that comes from here till it hits the wall there. then it bounces up, reflecting this one, which goes 4 squares up. So it goes 4 squares up. So it goes from there to there. And then it reflects off of this wall and comes in like that. And if you want to see what segments you can get filling this in, we can do a light color like a yellow and do standard, and we can do the spline, and we can do it with the fill. So we can start here. Oh, no, I'm using that, we can see everything from, I can certainly cover this. I can cover this. I can cover this. That actually makes me quite happy because when I look, this is this inside triangle that is all covered from this yellow. This yellow makes one bounce where it crosses the floor and another bounce where it crosses the white wall. I might, just so that we see the triangle that we were trying to fill it here in a different color. Yeah. Escape. Does that make sense? So for this room, certainly putting the camera in this spot up here where we started, which was just a random spot, worked. So what do we think about these Wayne Enterprise cameras? Do we have anybody who's a fan of the Joker or Harley Quinn, or, so are we rooting for Bruce Wayne or are we rooting for other people? Just like yeah, which actually, the comment where they say it's like a science project with mirrors, probably 6 years ago, we actually did a workshop, I think, in Kayenta, and we brought in mirrors, and you can set up experiments like this with mirrors that you can get from Home Depot or Lowe's or a similar store, like they use for tiles on walls, and bring them into a classroom, and you can put pretty things, or dinosaurs for little flowers, pretty rocks, and you can have students arrange and look at the mirrors. That works well. You can go down to 3-year-olds, enjoy looking in mirrors, looking at the reflections, and you start turning it into math as soon as you start asking them to predict what will you see if we put 2 mirrors at an angle, and then if I set the dinosaur here, how many dinosaurs will you see? And so it both has this artistic feel where there's something really beautiful that they can look at and that can hopefully capture the imagination of some people. By the way, if you wanted to do something like this with students but you didn't have access to mirrors, this is the kind of thing you can ask us, and I could probably send you a box of mirrors. we can provide some supplies to help you run activities with your classes and provide some mentoring. So, in fact, the Joker walks into a design company, into an architecture firm. And what the Joker would want to do is design an art museum so that these wing arms don't work. I think I'm out of time here, but I'll just posit that as a question for you to think about. It's actually a really famous mathematical question. No. Of course, he has a secondary issue here. He knows that Batman uses sonar when he fights, and so if he could come up with the space and convince architecture firm to design a museum where sonar doesn't completely work, then he's really ready for his plans. So yeah,